Hi, everyone. We're going to get started now. And just to start up front, this meeting is going to be recorded for those who aren't able to join live. And I will post links for the video on Canvas. Great. Well, thank you all for joining online. This is, I'm sure, a new experience for everyone, including myself. Not only is it my first time teaching online, it's actually going to be my first time teaching this course. Yeah, so I'm sure it's going to be a good adventure. Before we start, I wanted to quickly go over some of the Zoom capabilities. Basically, pretty simple stuff. I'm sure everyone is able to find the mute and video buttons, so you're welcome to turn on your video if you want, but if it does start slowing down the stream, I'll probably ask people to leave their cameras off. The other functions to keep in mind are the chat. You can ask questions through the chat if you don't want to speak up in person, and I will have our TA, Facundo, who's also here. He'll be monitoring the chat as well. Right.
Hi, Alan. Hi, everyone. I am Facundo, TA.
Yeah, and if you want to really quickly introduce or say anything about yourself, you can go ahead.
Okay, thanks, Alan. Well, I am a master's student in the energy graduate group, and I will be help Alan with the TA for this class. So you can contact me through Canvas. You're going to have my email, and we're going to schedule the office hours also for homeworks and the final project.
Great, thanks. And just a little bit about myself. I'm a faculty in the Transportation Technology and Policy graduate group, as well as the Energy Systems graduate group. I did my doctorate, let's see, 5 years ago at Carnegie Mellon in engineering and public policy. And most of my focus is on transportation and energy. So there may be a little bit more emphasis on that subject because it's what I know. Okay, yeah, so hopefully everyone is able to access the chat. And then the last thing is that you can actually participate. Hopefully, I think there's a raise your hand button in the participants. Under the participants, if you bring that up, you should be able to raise your hand, and that will bump you to the top of the list, and we can either call on you for comments, or again, just let us know through chat. Okay, great. So that's some of the Zoom stuff out of the way. Okay, so big elephant in the room, coronavirus. So I think this is a pretty interesting time for everyone. And I think that in terms of priorities, right, everyone's here to get a education, hopefully, but I totally understand that it may not be your highest priority right now, and that's okay. So during these times, I'm really hoping that you guys don't get stressed too much about grades. And if you're at all affected by the virus, just don't hesitate to reach out to me, and we'll be able to be flexible with how we're handling both grades and participation and tasks for the class. Yeah, and so again, even if it's not necessarily related to the course, you're welcome to contact me if you have any questions or concerns, both about Davis or life in general. So, okay, with that, I'm gonna quickly sort of shoot through the course logistics. I know it's all sort of in the syllabus and on Canvas, so I'm gonna try not to spend too much time here, but it'll be worth quickly going over. So 10 weeks of class. These are the basic topics we'll be covering. The first couple weeks is an overview of energy environment issues. So this is all pretty high level stuff and concepts that'll be important to think about. In the second sort of quarter part of this course, we'll be talking about energy resources and technologies. We'll be doing a bit of a deeper dive into each of the energy types and technologies that we use today, and see the sort of related policy concepts associated with each of these energy sources. In weeks 6 through 7, we'll talk about energy demand and other aspects of energy systems, thinking about not just a specific technology, but how it applies into a system as a whole. And then in the last couple weeks, we'll talk in a lot more detail about historic, current, and potential future energy policies and how that's going to affect our energy system. And lastly, we will, in the final week, have a class presentation of the students' final project papers, which I'll talk about in a moment. There's going to be 3 assignments in this course. Each of the problem sets are due 2 weeks after they're assigned. So these are I believe these are the due dates for each of the problem sets. We will have a midterm at the end of April. And then, as I mentioned, a final term project, which will be a written report plus an in-class presentation by each team. And when I say in class, I mean online, because we're not actually in class. And there's not going to be a final exam. So the course project consists of teams of 4 to 6 students, and you're going to be working with expert mentors on energy-related policy issues. So I've already come up with 15 or so energy issues, energy-related policy issues, and each of the mentors are currently helping put together a short sort of primer so that you guys can all get familiar with the topics. And I haven't figured out yet, but we'll have some sort of selection process. Everyone can maybe rank what they're most interested in, and then we'll assign everyone into groups of 4 to 6 students. And each of these mentors, they're all great. They have a lot of experience with dealing with these energy concepts. And so, let's see, the project timeline, once the write-ups are complete, I'm going to post them on Canvas, and it'll be everyone's responsibility to kind of go through those. I'll set up maybe some kind of online survey that everyone can take that can rank all the choices, and then we'll assign groups. Once the teams are formed, we'll post all of the assignments, and then you're going to contact your mentor to set up an initial meeting. The main deliverables are going to be a 1-page abstract that's due on April 22nd, a more detailed outline of the final report due on May 6th. And then in the final week, as I mentioned, there'll be the PowerPoint presentations, which we'll do through Zoom. And then on the last day of finals week, the final written reports are going to be due. So all materials are going to be posted on Canvas. So lecture slides I usually post after lecture, although I've had a couple requests about lecture slides before. So I will do my best to maybe post them just before lecture starts. Okay, sorry, I see a question in the chat. whether the final report is going to be written individually or as a group. It should be done as a group. So I know that's going to be tricky because obviously no one's going to be able to contact each other in person, but hopefully we'll be able to set up group meetings on Zoom and sort of coordinate the tasks online, which again I know isn't ideal, but hopefully it'll be a little bit less work than having to do every individual doing their own report. Okay, so going back to course materials, as I mentioned, recordings of the live lectures are going to be cross-posted on Aggie Video and on YouTube. And then lastly, I'm going to try and include supplemental reading material. Used to be mandatory, I guess, in this course, but it's just going to be supplemental here. If you're really interested in a topic, I think a lot of it will be pretty interesting reading material. All the submissions for class are going to be made through Canvas as well, so we will have some class quizzes that are going to be administered. All the homeworks must be submitted, and we're going to ask for them to be a single PDF file. So that'll be a lot more manageable for me and Facundo to be able to grade everything. And then lastly, the midterm exam is going to be administered through Canvas as well. We're still kind of working out exactly how we're going to do it, but obviously it's going to be a quote unquote take-home exam. In terms of the grading, 30% is going to be problem sets, so each problem set is worth about 10% of the grade. Class participation, which is like a historical artifact of actually being in class, but we're going to be flexible here. I think it's going to be essentially a sort of free 10% for everyone. The biggest component of the grade is going to be the class term project, which is worth half the grade. The term paper will be 40%, and the presentation is going to be 10%. And then the midterm is going to be worth the same as a homework. I'm notoriously bad at or slow at grading homeworks. I've been doing better at this, but it may be a little bit slower. Hopefully Facundo will be able to keep me on track. These are a couple sort of basic online resources that I just want to put out there that give a lot of nice sort of introductory resources about energy-related topics, and some reference material for things like units and conversions and things like that. So the first two links in particular are helpful for that. If anyone's interested in getting sort of more involved with sort of student organizations related to energy topics, studentenergy.org is a nice sort of repository for organizations across different campuses. And actually UC Davis didn't have one as of like a year ago, but a couple of grad students in the energy program were pretty interested and active in wanting to start one. And so now we have a UC Davis student energy chapter. So if anyone's interested, you can go on that website and check it out. And I'll actually have one of the representatives come in maybe at the beginning of next lecture to talk about it in case anyone's interested. Okay. So I think that kind of concludes the basic overview of course logistics. I'll pause really briefly to let anyone pipe up if they have any questions. You can either unmute or chat. I'll just wait a couple seconds, and if not, we'll move forward. Nope. All right. No questions. Everyone's good. Everyone's clear. Okay. So today we're going to be doing a pretty high-level overview and sort of motivation about what the energy system across the world is like today, and current sort of big issues that we think that are currently facing our energy system, and things we'll need to think about in the future. Okay. So what are our current energy sources? We sort of break this down into three major categories. This isn't sort of totally comprehensive, but this will be pretty much most of the energy that is being used by humans today. So we use a lot of fossil energy. Actually, the vast majority of the energy that we use and produce comes from fossil energy. So the big ones are oil, natural gas, coal, and some of these actually can be derived from unconventional fossil fuels. This usually refers to different forms of oil, heavy oil, oil sands, oil shale. You may have heard of these, and we'll go into deeper detail about these in future lectures. Renewable energy, and so this is a different type of energy source, right? That's derived from either the sun or the earth itself. So you have solar, wind, biomass, which is from plants, but the sort of beginning energy source of plants, right, is also from the sun, which is why we consider it renewable energy. Hydropower, and that's different from ocean power. Hydropower is usually coming from the damming of rivers and lakes and that sort of thing, whereas ocean energy coming from tidal forces and waves, and actually even differences in temperature between different depths of the ocean. So these are a potential, but currently pretty small, unrealized energy source. And then you've got geothermal energy, which is heat trapped underground that you can essentially take advantage of. And then the last category is nuclear energy. You have both fission and fusion. All of the current energy being provided by nuclear power plants today is all fission. There actually there's no such thing as a fusion nuclear power plant as of yet. Yep. So that's the basic sort of sources of energy that we have to work with currently. Okay. In terms of types of energy, we like to sort of categorize them across the life cycle of the use of the energy into what we refer to as primary energy, secondary energy, and useful energy. So primary energy is the naturally occurring resource. So it requires it means that there's no processing of the energy by humans. And so those original sources are things like coal, crude oil, solar, wind energy, and our collection of primary energy is used in such a way that we take that energy and transform it ultimately through secondary energy and useful energy to get what we want out of it. But primary energy is the thing that occurs without any human intervention. Secondary energy are intermediate sources of energy that's derived from primary energy. So, for example, electricity, when you burn primary energy, one of the ways that we take advantage of that is to generate electricity. So that's a form of secondary energy. Gasoline, for example, is refined from crude oil. And therefore is a form of secondary energy, not primary energy. Ethanol being processed from biomass is another example. And the reason why something like electricity, for example, isn't considered useful energy is because we want the electricity to provide some kind of service. Electricity in it of itself isn't actually doing anything. And so that's not considered useful energy. And so the ultimate form of energy that's useful to us are things like lighting, heating, and motive power, right? So when you're actually moving an object, such as a vehicle, that's all considered sort of the final form of useful energy. So these types of energies, this concept will be sort of important to keep in mind to sort of distinguish, sort of original sources of energy to what they're sort of being used for. And that will play a part, you'll see in a bit, on importance of things like efficiency as we go from primary energy to useful energy. So this is a diagram of energy systems sort of going through from your energy sector all the way to the final energy services that are being provided. And you can see right at the top is where you start with your primary energy, treatment and production. That's all sort of on the upstream. And as you move down, you go from your primary energy conversion to secondary energy to final energy and then useful energy. And so there are a variety of different types of primary energy and fuels that you can see up at the top. Hopefully you'll be able to see my cursor here. And the transformation of the primary energy to, for example, electricity from coal going through the power plants, and then the end use of these different technologies, whether it be a computer, light bulb, air conditioner, the type of energy that it's using or producing right at the end is shown in the useful energy bar here. And so this is kind of a high-level schematic, again, which we'll go into greater detail later on, so that you can see the transformation of primary energy to your final useful energy and the kind of energy services that they're providing. Okay, so before we get into too much detail about impacts and systems, first we need to get a little bit more fundamental and do a quick refresher on concepts of energy and power. Okay, so how is energy measured? So the most common is the joule. There's also watt hours, British thermal units, calories. There's also EV, which is not something that we'll be talking about in this class. Okay, so starting off with joules. This is the most common way of talking about energy. It's the sort of gold standard, right? These are the SI units for energy, and we use joules across a wide variety of applications and fields, so in physics and chemistry, biology. Hopefully everyone has seen this before. So the definition of 1 joule is that it's able to heat 1 gram of water by about 1/4 degree Celsius, or it can move 1 kilogram, 1 meter at 1 meter second squared acceleration. So the next common one that we'll see referred to here is the watt hour. And this is most commonly seen in electricity. This picture over here is a picture of a meter, which measures how much electricity is being used in your home. So this measures the amount of energy used at a constant power rate over a period of time. So the idea here is if you've seen like a light bulb before that has like a 10-watt rating, that means that when you turn the light on, it's using the power it consumes is 10 watts, which is equivalent to 10 joules per second. So if you multiply energy over time by time, which is the hour, then you get back to energy. And it's a sort of convenient way of measuring sort of levels of energy that are common in electricity. So 1 watt hour is equivalent to 3,600 joules, or 3.6 kilojoules, right? So that's 1 watt for 1 minute is just 1 joule per second for 60 seconds, so 60 joules. And if you multiply 60 by 60 minutes over an hour, you get 3,600, which is where that number is derived from. So as I was mentioning, it's very common in electricity to measure in these units. And so at the residential level, we measure, as you see in this meter, by kilowatt hours. One other type of energy unit that is common for certain aspects of the energy system is British thermal unit, or BTU. So this is used to measure energy content of fuels. It's basically an imperial rather than metric version of the joule. It's the amount of energy needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So 1 BTU is just about over 1,000 joules. And it's most commonly used for natural gas. So an MMBTU is 1 million BTU. So 1,000 cubic feet of natural gas is just about 1 million BTU. A therm is 100,000 BTU, and that's 100 cubic feet of natural gas is 1 therm. So when we're talking about natural gas as a fuel, oftentimes it won't be referred to in terms of joules. It'll be referred to in terms of BTUs. The last one is for large economy-wide energy usage. And so this is talking about on the order of, if I were to say the energy consumption of the United States annually, or like California annually. One common way or common unit that people will talk about is quads. And so that's 10 to the 15th BTU or a quadrillion BTU.
Alan, we have
Yeah.
a question.
Oh, yes. So we have a question. So why is natural gas measured in feet? So it's in cubic feet. So it's a measure of volume. So it's like 1 foot by 1 foot by 1 foot, right? And so we're talking about fuel in terms of volume, and that's because it's a gas, and so it also has when we talk about sort of gaseous fuels, you actually need to know the pressure as well. But we commonly, I believe, think about these in terms of just 1 atmosphere, and so 1,000 cubic feet should be referring to a volume of the gas, which tells you how much gas there is. So there's a question, so not considered mass instead of volume. Yeah, so that's a good question. Actually, mass would probably make more sense from a, I don't know, scientific perspective, I guess. But I'm not 100% sure, but I'm fairly confident that the reason that they measure this in volumes rather than mass is for practical reasons, right? It's really hard to, if I'm transporting like gas or have a pipeline for natural gas, it's a lot harder to measure the actual volume than, or sorry, it's a lot harder to measure the mass of that fuel than it is to measure the volume. So I think that's probably one of the reasons why it's using volume instead of mass. Yeah, that's right. So mass is a lot easier for liquids. Although I will say, even for liquids, we typically measure in volumes as well, right? So if I go to fill up my gas car, that's usually done by gallons of gas, not by pounds or kilograms of gasoline. Okay, moving on. The last energy unit that we'll talk about are calories. And so I'm sure folks have seen calories before. This is most commonly used to measure energy content of foods. Similar to BTU, but in metric, so that's the energy required to raise the temperature of 1 gram of water by 1 degree of Celsius at 1 atmosphere. So if you'll recall, 1 joule raises it by 0.24 degrees Celsius. And so 1 calorie is just about over 4 joules. One of the things to keep in mind here is that calories on food labels are actually not what we're referring to as calories here. They're actually kilocalories, so those are thousands of calories. So that'll be important to keep in mind. So like, let's see, a 2,000 calorie, they say you eat 2,000 calories a day. It's actually 2 million regular calories, which would be about 8 million joules. Okay, so we're going to test out some functionality here. So can you guess the energy content of each of these different things? And so I have prepared a poll. So hopefully folks will be able to see this. Okay, so you should be able to view the energy content poll, and you can see how well you can guess about each of these different things. And so I'll wait a second for folks to fill these out and submit them, and we'll see how well we do in a moment. It's a nice sort of high level order of magnitude estimation. See how much people know. I see we have someone saying we should have a I don't know option. Well, it's not a quiz or anything. Just kind of curious to see how people are doing. So EV battery, so that is an electric vehicle battery. Yeah, so I see some, another question, will I be posting the slides? Yes, so actually, I think I posted the slides on Canvas already just before the start of class. And so I'll try and post the slides just before class begins every day. Which I now realize will have the answers to all of these, but hopefully you guys aren't looking at that. Doesn't really matter because it's not a quiz or anything. I'm seeing that no one has finished yet, so we'll give it a little bit more time. Either that or no one's paying attention to the lecture, but oh, it looks like, okay, well, apparently people have submitted it. I don't know why it's not showing up for me. Well, okay, well, since people are saying that they've finished, I'm gonna end the poll. And Well, I guess we're getting our first Zoom hiccup. Let's see. Share results. Huh. All right then. Well, I guess that didn't work out so well. Okay, well, anyways, hopefully you guys were able to see your own answers. I don't know why that's not working. Not my fault. It's something wrong with Zoom. It's the Zoom built-in polling feature, but that's all right. So you can see how well you did over here. This will give kind of a rough sense of the energy content. So the meal, I think, is maybe the easiest, right? We were talking about, you consume maybe 2,000 calories a day. You just have to keep in mind that it's 1,000 or 2,000 kilocalories, not the actual calories that you see on the labels. The human body contains maybe 1,000 times that amount of energy. Coal and gasoline are both fossil fuels, which are really sort of energy dense, energy rich. And so they have relatively high amounts of energy. So if you consider one of the things that we'll talk about is the difficulties of sort of transitioning to renewable energy. And one of them is that the inherent energy density of renewable sources is just quite a bit lower. Okay, and so if I think about the amount of sunshine on a patch of ground 1 meter squared for an hour, so not even taking into account the efficiency losses of collecting that energy, that raw sort of primary energy coming from the sun is about between 1 to 10 megajoules, right, order of magnitude. And so, coal and gasoline are 10 times higher for, a kilogram of coal or a gallon of gasoline compared to, 1 hour of collecting solar energy. So you need to do it for something like 10 hours of solar to collect the equivalent of like 1 gallon of gasoline. An EV battery, so if you know the energy content of a gallon of gasoline, you can probably guess at what the EV battery is, right? So you can think about, maybe an average car is 10 to 20 gallons of gasoline. So you probably want to get the same sort of range or same order of magnitude as the range, 10x that. So it's 100 to 1,000 megajoules. Yeah, okay, so there's a question here. Would the energy content of sunshine be the same as that on a photovoltaic solar cell at the same time? So yes, so if you have no clouds and everything and you put your solar cell out in the field, the amount of sun power hitting the solar cell is going to be equivalent, right? Because it's going to be the same as if it were just hitting the ground. But the amount of energy that you get out of the solar cell is not 100%, right? You have losses from the solar panel. And so you're going to collect some smaller proportion of the energy of the sunshine. In terms of energy consumption of a household, so typically, the metric that I sort of have in my head is that on average, the average household in the US uses about 1 kilowatt of power on average. So across a full day, that's something on the order of 20 to 30 kilowatt hours. So you're on the order of 100 to 1,000 megajoules. So now a little bit more extreme examples. So if you had a nuclear explosion, the amount of energy released is 10 to the ninth of that. And so you could probably power all the households in the US for a day with a nuclear explosion. The annual consumption of energy across the whole country is 100 quads, or about 100 exajoules. And the worldwide annual consumption of energy is about 10 times higher than that. So measured in watt hours, about 100,000 terawatt hours, or 100 to 1,000 exajoules. Okay, and I'm gonna sort of breeze through this slide. These are just some reference points for folks to see. This may be useful in future assignments. And I have some other reference slides that you'll be able to use as well. But this gives a rough estimation of energy content of a lot of the primary fuels. Okay, the next concept we have to get familiar with is power. So power is the rate of doing work. So it's just exactly what we were just talking about with energy, but you divide it by some unit of time. So the two most common ones are watts and horsepower. So watt, generated or invented by this gentleman here, watt, is the SI unit for power. As I was saying before, it's 1 joule per second. Okay, so this is really commonly used in electricity. We can use this to describe, for example, the capacity of a power plant. So if a power plant has an installed capacity of 10 megawatts, that means it's physically able to produce up to 10 megawatts of power instantaneously. So certain types of power plants, for example, nuclear power plants, they will produce up to their nameplate capacity, which is this capacity number that I'm talking about, most of the time, because they have to stay on. Whereas solar and wind, for example, are resources that are only generating at their capacity when the fuel is available. So when it's sunny outside during the day, or when it's really windy, when that particular system is operating at full capacity, then it'll be operating at its nameplate capacity. But when the sun isn't shining, right, then you won't be producing power at the capacity that it's rated at. So the other metric is horsepower. So I'm sure a lot of you guys are familiar with this. So this is commonly used to describe engines. So a single horsepower is able to lift 75 kilograms, 1 meter in 1 second. It can be a little bit confusing because actually a horsepower can mean different things. So imperial horsepower is about 745 watts, whereas a metric horsepower is about 735 watts. Where does the term horsepower come from? Well, you might think that it describes the output power of a horse, but actually the peak power production of a horse is about 15 horsepower. So a little bit disingenuous. Actually, the reason why it's called a horsepower is the average power production of a horse is about 1 horsepower. Yeah, so good question. For the class, will we be using metric or imperial measurements? So you're always safe to go with metric, as long as the sort of answer is correct. It doesn't really it doesn't really make a difference if you're reporting things in watt hours or joules or watts versus horsepower. But I would say, for convention's sake, what we'll probably ask to do is, for any particular application, you want to use the sort of units that are associated with that. So if we are talking about like an engine or something, then it makes more sense to talk about it in horsepower. If we're talking about power plants or well, basically almost any other sort of power unit, then it makes more sense to talk about watts. So I'm not going to be too strict about that, but it's good to keep in mind the convention, because that's what's is used when you're being conversant about it, and it'll make the most sense when you're talking to people actually in the field, that you say, oh, the power plant is operating at X watts, not at Y horsepower. Okay, I'm not going to do the poll this time. We can quickly sort of just move through these, and so maybe if you quickly have in your head an idea of what the power of each of these things are, then we can see how this sort of relates to your preconceived notions, right? So light bulbs, I think most people are going to be pretty familiar with. With sort of newer age light bulbs, you're talking about LEDs or CFLs, and those are usually at the lower end, sort of 5 to maybe 20 watts. If you remember back in the early 2000s and in the 90s, if you're a dinosaur like me, then you'll remember incandescent light bulbs, which are much higher wattage. You're talking about sort of 75 on the low end, all the way up to 200, maybe even 250 watts for a light bulb. And so the efficiency of these things has really improved. And we'll actually talk about some reasons why that happened, that transition happened. If you're an exercising human, you're putting out constants, maybe 50, 100, maybe at the upper end, 150 watts of power. But it's really hard to sort of consistently have an output power above 200, 250. You'll get gas pretty quickly. Microwaves are about 1 kilowatt, 1,000 watts, a fairly high power draw application for homes. You're not constantly using like a microwave, right? And so there's a difference, even though a microwave uses we'll say 10 to 100 times more than a light bulb. Your light bulbs are probably on a lot longer than microwaves. When we talk about energy consumption, the lights in your house probably use more energy than the microwaves. A solar panel. So if we're just talking about maybe a rooftop unit, one of those panels would probably be around 300 watts. And then if you're talking about utility scale solar, so those are like the big fields of solar panels that you might see out in the wild, those will vary between 100 to even like the really, really the biggest ones are getting to the order of gigawatts, but usually they're going to be more on the smaller end of that 100 to 1,000. As I mentioned, the average household uses about 1 kilowatt of power in the US. When you talk about other countries, and I'm thinking particularly about third world developing countries, that number could be quite a bit lower. In terms of energy consumption per capita, United States is probably among the highest in the world, if not the highest. Car engine, anywhere between 100 to 1,000 horsepower. You're probably not going to get to 1,000 horsepower unless you're really rich and you own like a Bugatti or something. And so that in terms of metric units is 100 to 1,000 kilowatts. So wind turbines, so these can be pretty big. Individually, these things can vary 1 to 3 megawatts. And the 3 megawatt ones, actually, I've been informed that I should update this. There are actually ones that are offshore, which means they're sort of built out in the ocean, that are actually way bigger and can get even up to 5, even 6 megawatts. So those wind turbines are absolutely massive. Each blade is the length of a football field, just to give you a sense of scale. But the ones that you see around sort of on land are more on the order of 1 to 3 megawatts, and even the 3 megawatt ones are quite big. You're talking about blades maybe 100 feet, 150 feet in length. If you have a full wind farm, you're often talking about hundreds or even thousands of these turbines, which adds up to quite a bit of power production. Natural gas plants. So these are probably the most prolific power plants, fossil power plants in the US these days. Produce anywhere between 10 to 1,000 megawatts. And they can be built very quickly and produce quite a bit of power. Coal plants are typically a little bit bigger. Not always. There are natural gas plants that sort of rival coal plants in scale, except for some of the very biggest ones. And then you have nuclear plants, which are similar in scale to the largest coal plants in the country. To give a quick sense of scale, the peak California power demand is about 50 gigawatts. And so, right, it's not always like that throughout the day. You have a lot more usage when people are, turning on computers and lighting, and air conditioning and heating is a really big one. Air conditioning in California. And so during peak time, on certain days in the summer, when lots of people have AC running, you can hit as high as about 50 gigawatts of demand. And then if you took all the power production, all power plants, all solar, all wind, all that stuff, and you add it all up, the total installed capacity of power in the entire world is about 15,000 gigawatts, or about 15 terawatts. Okay, so primary energy use and energy-related emissions are projected to grow very rapidly over the next century, especially in developing countries. So to give some sense of the correlation between energy use and population, here we can see relative population density across the world. Okay, and so these are number of people per square kilometer. And if I go to the next slide, sort of keep in mind where the sort of darker areas of the world are located, aka where population densities are. You'll be able to see that there's a pretty high correlation with energy use, right? And so this is just lighting of cities that you can see from satellite imagery, and it's highly correlated to where the people are, obviously. And that speaks to, I think, a lot of the future challenges of the energy system. So diversity and security of energy supply, air quality and pollution, and global climate change. So it's really important to distinguish 2 and 3, okay? And so when we burn fossil fuels, for example, that releases a lot of emissions into the air. And there are sort of 2 categories of emissions, ones that affect air quality, and these are what we refer to as sort of local pollutants. So these are things like SOx and NOx, and they affect air quality. They can degrade the air quality through increased morbidity in respiratory systems. So you have higher rates of asthma, respiratory diseases, and even deaths where you have bad air quality. And that's really different from other pollutants such as carbon dioxide, such as methane, which don't degrade local air quality, but can result in a greenhouse gas warming effect, which damages the global climate change environment. So we'll need to think about both of these things when we think about the future provision of energy. So I'm going to quickly sort of go through issues associated with all 3 of these in a little bit more detail, sort of as motivation for everyone to think about why it's important that we think about the future of our energy system and that we don't just sort of take it for granted. Okay, so the amount of energy that we consume has sort of exploded since the Industrial Revolution in the late 1900s. So this is a nice little chart of primary energy consumption by source. So traditional biofuels, what does that mean? So traditional, it's just wood burning, right? So we use wood for heating, and in centuries past, we would use it not only for heating, but also for cooking and also for light. And that amount, even though we've sort of detracted and have other energy sources today, that amount actually hasn't changed too much. It's actually, if anything, has increased a little bit. And that's because population growth and many areas of the world still do use traditional biofuels for their final useful energy and energy services. There's been a very large growth in coal, especially for power production. You used to see a lot of that being used in things like motive power for trains, but now I would say majority of it is being used to generate electricity. Crude oil is big for transportation. Obviously, we reform or produce gasoline from crude oil, and the vast majority of this is going to be for petroleum use in transportation. Natural gas is also a big one, and actually I'll show a graph in a little bit about how each of these primary sources goes to end use. But you can see basically a order of maybe a little less than 5,000 terawatt hours going up to maybe 150,000 terawatt hours in the span of 200 years. Oh yeah, okay, I see a question here. What types of people use wood burning? Yeah, so a lot in developing countries use wood burning for cooking still. So cook stoves in many developing countries are powered not by gas or electricity that we see more commonly in developed nations like the U.S., but also for but they'll use wood to basically do a lot of the cooking. And biofuels are used in a variety of other applications as well, but I think cooking is one of the big ones. The share of energy has changed drastically, though. We can see, so the yellow line is the traditional biofuels. You can see a big growth in coal that's decreased over time, and the ones that have sort of really increased. So since the 50s, there's been a growth in nuclear, but besides that, gas and oil have really sort of taken off. And this graph only goes out to the year 2000, but if you look at a little bit more recent trends, coal has fallen even farther, and gas has sort of spiked up, and we'll talk about that in future lectures. The yellow trend line again is traditional biofuels. So if we look at the primary energy consumption of the US today, you can see what it looks like in 2018. So natural gas and petroleum account for about 2/3 of the primary energy. If we were to look at this graph maybe 7 to 8 years ago, your coal number would be significantly higher. You're maybe at natural gas and coal would probably be flipped, actually. And again, this is a topic we'll cover later, but there's been a big transition away from coal thanks to fracking. So in chat, I see question, percent of primary energy graph on the last slide. So that is for the entire world, not just for the US. Yeah, so then when we think about renewable energy, I think one thing that often surprises people is that you see a lot of news about growth of renewables, and the growth has been sort of really tremendous over the last 10 years, and yet still the majority of renewable energy actually is coming from hydroelectricity. While solar and wind have grown tremendously, they still are a relatively small proportion of the total power production. And so when I think about solar and wind, yes, it's like 30% if I add it all up, but it's 30% of 11%. And so it still has ways to go, but there's a lot of potential for it. And I think that we'll see that number continue. There are certain regions in the country, such as California, where it is actually quite a bit higher. And again, that's something we'll delve into more detail on when we get to the renewables lecture. Okay, so this is a Sankey diagram. And so this is a sort of nice breakdown of all the primary energy sources on the left going to the energy services on the right. And so you can see sort of how everything is sort of broken down. One thing that you'll note is that they have this nice little intermediate of electricity. And so we can see that, you know, all solar, all nuclear, all hydro, all of wind, and the vast majority of coal, all of those sources are being used to produce electricity. Okay, natural gas is a little bit different. You have a substantial proportion of natural gas being going directly into some of the end uses in residential, commercial, and industrial sectors. And so what is that? So if you have like gas heating, or you have a gas stove at home, that cooking energy is coming from natural gas directly. Commercial and industrial applications will often use, natural gas. They'll have heating operations, cogeneration. They can be producing electricity on site, which may or may not be counted in this intermediate bar here. So actually, there's a very substantial amount of natural gas being used in electricity generation, but also a large portion of that is actually going to the end sectors directly. Petroleum, vast majority is in transportation, as I was saying before, gasoline to power your vehicles. Some small portion actually does go into like electricity generation for like oil-fired power plants. Right, and then the last bit of interesting thing to note here is that if I added everything up here in terms of the total energy content, your final energy services would only be a small fraction of that, right? And that's because we actually lose about 2/3 of the primary energy content once we go to our final energy services. And that's mainly lost through like heat. So if I were to like combust coal, for example, you produce electricity, but a lot of the energy is simply lost to heat. And that's a pretty similar trend globally. That last Sankey diagram was for the United States. This one is across the world. So we look at primary energy breakdown. So you have oil, coal, and gases are sort of three big ones, same as in the US. You do see a larger chunk of biomass, and as I was saying before, due to use in other countries where the proportion of biomass is higher. And then in the final energy here, compared to the useful energy, again, you're losing about 2/3 of it because of inefficiencies in the system or inefficiencies associated with conversion of one energy type to another. Renewables have been growing pretty rapidly. As I mentioned, you can see that sort of orange slice here. So yes, it's a really tiny sliver, but sort of percentage-wise of growth, it's by far sort of the largest growth, besides maybe natural gas in the last couple years.
Alan, there's a question about.
Yeah, good question. So energy types, are energy types equally inefficient? No. So we'll get into some of the issues of efficiency in further lectures, but there are ways in which energy conversion from one fuel to, say, electricity can differ quite a bit between fuel sources and even technology types. Yes, okay, I see another question. Renewable energy equals clear energy? I'm not sure what that means. Oh, clean, okay, clean energy. Yeah, so that oftentimes they are correlated. So yes, when we talk about renewable energy, thinking about things like solar and wind, we often call them clean energy because the sort of marginal production, I mean, that is to say, like that last unit of energy that I'm producing is essentially emissions free, right? I get like things from the sun or things from energy from the wind. That doesn't produce any emissions per se. So typically, renewable energy is clean energy, which isn't to say that that's kind of the defining aspect of it, because in theory, you could make fossil energy clean. It's very difficult. You would do something like what's called carbon capture, where you take the emissions and you go through some chemical processes to convert it into like a solid, and then you could like bury it or sequester it, right? And technically that would be clean. And so not all clean energy is renewable energy, but renewable energy oftentimes is clean energy. That having been said, one of the things we'll cover in this class is thinking about the upstream implications, sort of a life cycle. And so what does it mean to actually produce the solar panel or the wind turbine, thinking about the production of it, as well as the impacts on material mining and that sort of thing. And so it's good to be sort of holistic when thinking about these topics. People will say, for example, electric cars have zero emission, which is, technically true from the perspective of like a tailpipe, right? You plug in the car and it's not doing any combustion in the engine, because there is no engine. But the electricity that's being provided into the vehicle, maybe it's coming from a solar plant or a wind farm, or maybe it's coming from a coal plant, right? And so we need to think about these things when we want to be realistic about the emissions impacts and the supply chain and material impacts of any particular technology. And so that's definitely something that we'll talk about later on in class. So here are global primary energy consumption shares, sort of more recently. Oil demand has gone down somewhat, coal demand as well, and natural gas has been increasing. Yeah, I've shown a couple examples of these already, but I'm sure we'll all become pretty familiar with these trends as class goes on. This is a higher level view looking specifically at renewables, so solar, wind, hydro, geothermal in different countries. And the main gist here, right, is that over the last 2 decades, we've seen a really sort of rapid growth in renewable energy production and consumption. And so, despite what I was showing before, where, in a overall sort of share of energy production and consumption, it's pretty small, right? Which you can see here, the percentage, anywhere between 1 to 10%, 12% at the highest. On the other hand, it is growing really quickly, and so there's some good things to see there. Biofuels production by region. So this is having to do with ethanol production, biodiesel production. So I'm not talking about like traditional biofuels of wood sources. These are liquid fuels derived from plant matter, and so that has grown pretty dramatically over the last several decades as well. And I'm not going to go too much into this right now, but we'll talk about some of the policy reasons that has led to the growth in biofuels later on the line. We can see major oil trade movements. So these are trade flows between countries. You can see both imports and exports in the US. And this gives some sort of, basically I want to give a high level view of how interconnected the global sort of supply chain is for not only oil, but also for natural gas and other types of energy flows. Sort of moving quickly through this, one of the things that is pretty interesting is thinking about the direct versus embodied energy in these trade flows. So direct energy is the consumed final energy. So that's like if I were to, import gasoline from the Middle East, we can see the size of that sort of flow of the final energy product into this country. And coincidentally, our largest import of gasoline and oil-derived products isn't from the Middle East. It's actually from Canada.
Alan,
Yeah. Okay. I see a question saying less consumption of renewable energy is good. Did I say that? I'm not making any sort of statements about whether it's good or not to consume a particular type of energy. I certainly don't think less consumption of renewable energy is good. But there are lots of other sort of considerations to think about when we think about our energy system. Okay, and so embodied energy is not just the energy that we're consuming directly from the final good that's being delivered through these trade flows, but is also thinking about all the upstream sort of production of associated with like the production of gasoline, for example. So that includes the like drilling and refining, all of that. And so the embodied energy includes all of those, the sum of all of the energy along the full sort of life cycle chain of any particular fuel that's getting traded across. And here you can see that actually the embodied energy is really high going into, is highest going into the US and into Europe. So these direct energy versus embodied energy will actually look pretty different. Okay, and we're going to go a lot more into detail about resource constraints, but this gives sort of a high-level view of what the available resources are for us to consume. So the annual world consumption is about this big, so the total size of that block there. And so that includes consumption of all different types of fuels like coal, oil, gas, so on and so forth. And this shows basically the reserves that are available, that we know are basically available across the globe. Okay, so I see a question here. What energy sources have the most or least interconnected supply chain? Well, I probably wouldn't be able to tell you off the top of my head. They're all, I would say most energy supply chains are fairly interconnected. So even a question like that would be maybe a little bit difficult to quantify. But I can look into this and get back to you. Okay, so going back to this slide, these reserves are basically what we estimate are left for us, and you can actually calculate based off of the US or the world consumption of a particular primary fuel today and see if we kept consuming coal at the same rate today, or if we kept doing nuclear power at the rate that we do today, how many more years could we do that before we actually ran out of the fuel. And we'll show some of those calculations later when we talk about the fuels specifically, but this should give sort of a high level overview of what those numbers approximately look like. And then when it comes to the renewable sources down here in the bottom, you can see the amount of energy coming from the sun. Okay, and so some of that is, or some small portions of the renewables coming from hydro and wind. You can also see their relative sizes compared to the solar energy. And then the amount of energy that's actually being captured by plants in photosynthesis can be seen in this biggest box, biggest sort of magenta box at the bottom. And so in terms of availability, solar energy is sort of the most prevalent, right? But that doesn't mean that it's super easy to access that resource, and that even if we could build lots of solar farms, you still have some difficulties associated with the fact that you can't produce power all the time. So what's everyone going to do at night? The actual getting the electricity from places where it's really sunny to places where people actually live can be tricky, and transmitting that power over long distances. And so, yeah, I think that there's great potential here, and that we're definitely going to see lots of growth of solar in the future, and that is kind of what we want, right, to address issues of climate change. But we're going to learn all about the sort of difficulties in getting to that in this class. Yeah, and so I was just mentioning how many years of supply do we have left. So a lot of the fossil fuels are going to be done or are going to be gone at our present rate of use, within a couple hundred years, and for transportation fuels, probably even sooner than that. Although these numbers will differ depending on who you ask, and they've changed over time as well as we get access to more resources that we didn't think that we had before. In terms of the traditional uranium, which is what we use today for nuclear fusion, you can use up to 1,000 years if you have certain types if you're using certain types of technologies. Deuterium, which is used for fusion, which we don't have yet, could in theory last for millions of years. And then renewables are indefinite, or at least until the sun explodes in 50 billion years, something like that. Yeah, and then in terms of renewable energy, how much do we have available? Yes. Okay. Oh, sorry. Deuterium. What is deuterium? I believe deuterium is an isotope of hydrogen, but it's a material that you need for nuclear fusion to occur. Let me see if I have it correctly. I think deuterium is the atom that undergoes nuclear fusion to release energy, and so if you use that, then it's sort of the equivalent of having uranium for fission technology. Okay, so what's available, what's exploitable? So in terms of solar, if you use 1% of Earth's land area, which is what a lot of sort of experts talk about with solar radiation, that's basically all you would need to get all the total energy demand today. So you'd need about 1% of the Earth's land area. For wind, there's actually quite a bit more of that resource, and actually wind is currently about 3 times more prevalent in terms of energy production than solar. there are economic reasons for that as well, which we'll talk about. But here, basically, you get a good sense of how much power there is actually available in renewable sources, and so, you know, to those who say that we can't actually produce all the power that we need from renewables, that's simply not true. You'd only need actually a fraction of the total potential available to produce what's annually used today. Okay, so that sort of wraps up a lot of the resource adequacy issues. Some of the other things that we need to think about for air quality and pollution related to power reduction today, and how to transition away from that. So pollution from transportation, this is New York City in 1973 versus 2013. And we'll talk about a lot of the policies that have transitioned our energy and emission systems to help clean it up quite a bit. And there's still a long way to go. But in terms of air pollution, it's actually a lot better these days than it used to be, despite the fact that there is higher amounts of travel, higher amounts of energy use. Maybe some of you guys have seen this. This is a series of pictures taken every day in 2013 in Beijing, and you can see so this is actually at the same time of the day every day for a couple months, and you can see that depending on sort of the local air quality and weather conditions, pollution can settle down into the city, and you can see a huge difference in the livability and air quality within the city. So this is a little bit old. This is from 2013, and since then, actually, China has put in a lot of effort into cleaning the energy system, and so you see, proportionally fewer gray days, which indicate lower sort of air quality. But China has a long way to go still in terms of improving air quality. But that is one of their large sort of policy pushes. This is I think thanks to a lot of clean air policies, aggressive air policies in both the federal and state levels. Or you might think about the efforts of the Environmental Protection Agency. So there's been a huge amount of progress in reducing air pollution from a lot of these particulates. So things like carbon monoxide, lead, nitrogen dioxide, ozone, sulfur dioxide. Some of these can create these volatile organic compounds, which are bad for your lungs. Sulfur dioxide can create acid rain. So a lot of these pollution particulates are now heavily regulated, and we continue to do so. And you can see the improvement, 5 to 10x improvement in the vast majority of these over the last 3 to 4 decades. And so there's been a lot of great progress, but a lot of populations still live in what we call non-attainment areas, which means they're higher than the recommended EPA thresholds for any particular particulate. And so we can see, continuing improvement even in the last 2 decades. So in California, a lot of the worst air quality in the country is actually in Central Valley of California. A lot of the pollution from Los Angeles will sort of move inland into the basin and kind of just sit there. And unfortunately, that leads to really low air quality. And then there are low air qualities in certain small counties of populated regions across the US. again, doing a lot better even over the last couple decades, but still being in non-attainment is pretty bad. And so these set of maps here are showing non-attainment over sort of a long average period of time, but oftentimes you're going to have counties on certain days of the year they're going to be in non-attainment, which is where you see that 56% number from before. As I mentioned before, air quality can actually lead to increases in morbidity, which are basically non-lethal sort of health events, and mortality, which are actual deaths coming from lower air quality next to specific types of power plants. And this is measured in lots of innovative ways. We have statistical means of measuring deaths attributable to power plants via lower air quality, and so this shows a sort of rough estimation of that. The air quality generally on the West Coast is a lot better because we actually don't have much fewer coal plants compared to the East Coast, and that's something that we'll show later as well. Air quality across a whole variety of cities. You can see livability is none of them are all sort of white, low pollution, right, according to World Health Organization guidelines. And so it's a pretty serious problem. And it's something that regulation is seeking to improve, not only in the US, but across the world. Okay, so the last one that I'm going to talk about is from climate change. So greenhouse effect. So this is solar radiation. Comes in, it's reflected by Earth in the atmosphere. But if you have a buildup of certain types of molecules in the atmosphere, then the amount of energy that's going to be trapped in the atmosphere is going to increase and raise the temperature, which leads to lots of adverse effects. Okay, so here, this is kind of a rough estimation of the numbers associated with the solar radiation and our climate. Okay, so 340 is a pretty good number to keep in mind, or easy number to remember in terms of solar radiation per meter squared. So it's 340 watts per meter squared. So if you were to draw sort of like a 1 meter by 1 meter square on the surface of, or right at the top of the atmosphere, you're gonna get about 340 watts coming through that at the very top of our atmosphere. And as it comes through, some of it gets reflected by clouds and the atmosphere, and then some of it gets absorbed by the atmosphere. The rest of it goes down, hits the surface. Some of the stuff on the surface gets reflected, and then a whole bunch of it gets absorbed. Okay, and so the absorption by the surface is going to increase the energy being absorbed, and that gets released as latent heat. And so you have that irradiation going back up to the atmosphere, getting absorbed, and that will bounce either out to space or back down. And so this is kind of our solar radiation system in equilibrium. So what happens when we consume lots of energy and we burn lots of fossil fuels and emit CO2 into the atmosphere? That increases the radiation that's going to be absorbed by the atmosphere, as well as the amount of energy that remains sort of trapped in here as it gets emitted back up from the ground. And that's going to lead to ultimately, the system will come back to an equilibrium where you're still getting, you know, a total of 340 out, right? If I added up all these numbers, you're going to get a balanced equilibrium, but it's going to be occurring at a higher temperature, and so that's what's leading to global warming. So hopefully folks are familiar with this or have seen this before. This is atmospheric concentrations of CO2. This is from an observatory in Hawaii. And this measures basically the concentration of CO2 in our atmosphere. And you can see this sort of cyclic up and down, but a really nice sort of obvious continuing trend increasing over time. And that's directly related to anthropogenic emission of CO2. We can see that what does that mean over the last hundreds of thousands of years, right? So it's absolutely true that our CO2 concentrations do fluctuate up and down, but you can see that there's probably something abnormal happening right at the end here. And that increase, right? This whole increase is over about a 100-year time period. And we're talking about a scale of hundreds of thousands of years. So that increase is really sort of unprecedented in nature. And we are, you know, we're able to measure the anthropogenic or human-induced carbon emissions that are sort of attributing to this increase. And this has also led to increases in temperature, which we can measure on the surface. And these increases are coming also from a variety of data sources. We can tell from tree rings, from ice cores, which are particularly sort of well known in this field for being able to measure the historical temperature changes over time. And you can see that over the last couple centuries that there has been a very sort of steady sort of temperature trend before a sudden increase at the start of about the Industrial Revolution. And then the strongest indicators of climate change are not only atmospheric temperatures, but also anomalies in sea level rise and from sea ice extent, which is basically the coverage of the ice annually, the ice melting cycle in the North Pole. And so sea ice has decreased quite drastically over the last half century or so. And as a result, the sea level has been pretty continuously increasing. Okay, so I think that actually I'm going to end for the day. I'm not going to be able to get through the rest of these slides, but we can pick up where we left off on Wednesday. I just want to sort of leave us with our sort of my final slide that I made here. I think I've been reading actually a lot of articles recently about the relation of climate change to coronavirus. That's left me, I guess, a little bit depressed. I think that understanding like systemic changes and exponential growth has been difficult for society as a whole. And that this current pandemic is helping to teach us about that. But I've also been reading a lot of articles that are talking about, you know, our inability to deal with coronavirus is similarly mirrors our inability to deal with climate change, and where we need sort of rapid response, we don't see that happening even in something as severe as coronavirus, which is happening very quickly, and that type of response that's needed is going to be even harder for something like climate change, which is a little bit more difficult to observe directly. Maybe it won't affect a current generation of adults, but maybe the next generation of adults. So they care less about it, and so hopefully this will be kind of a wake-up call for all of us. Yeah, and so I know that the coronavirus issue is definitely more of an immediate concern, but the climate change issue is going to be a similar, slower issue of magnitude, and hopefully that this class will motivate folks to think about these issues and maybe deal with them in the future. Yes. Okay. I'm seeing a whole bunch of questions pop up right at the end here. So before we end, I'll sort of address these. So have you heard of the EPA's new policy announcement from last Thursday regarding regulating pollution of companies? Yeah. I did see that announcement. Bit of a shocker, although it seems to me that at times like these, the administration is just trying to get away with everything that they can. It's a little unfortunate. It takes a step back from a lot of the really nice progressive things that we've been doing. And to me, it's unclear whether something like that is even really necessary. In fact, I think at the end of the day, it doesn't really matter. I think that the way that we as a society have changed in response to the pandemic, in sheltering at home and that sort of thing, has led to like way larger actually energy decreases as a result. And we can actually, there's a whole bunch of articles and papers coming out about how energy consumption and pollution has decreased as a result. People are driving a lot less. So yeah, even though the administration is like pushing these or reversing the anti-pollution laws, I think at the end of the day, the coronavirus, if there's any silver lining, is actually reducing pollution a lot. And whether we're going to be discussing energy policy affected during COVID-19, definitely, yeah. It's something that I'm trying to quickly get a handle on, but it'll be something that we'll talk about for sure during class. And then I see another question. Just to clarify, the class attendance portion of our grade does not refer to our Zoom attendance. Yeah, it's basically 3 points. Okay, like I think that that during these times, you participating and showing up for lecture, that's great. And that is sort of just indication of your interest in this topic, but I'm not going to hold it against anyone who may or may not be able to attend because of various circumstances. So don't worry about the participation grade. That's all going to be. We're going to be really flexible with that. Yeah, so will you be assigning groups for the paper presentation? Yeah, so I'm still trying to figure out what to do. I think in my mind, I think the easiest thing to do will be to put out a class survey and have everyone rank the different topics, and then we're going to assign based off of those rankings. And obviously, not everyone's going to evenly split into these 15 groups, so not everyone's going to get exactly what they want. But I do think that all the topics are pretty interesting and pretty relevant. And we'll touch on, and all of them are going to get touched on during our overall class. And so I think the way that we're leaning to do it is to be ultimately assigning the groups, but hopefully we'll be able to get at least your top three or four choices. Yep. Okay. Well, it is now 2 o'clock. I don't see any new questions. So I'm just going to say thank you, everyone, for attending. Thanks for putting up with this entirely new format, and hopefully this is going to work out for everyone. And if anyone's having any sorts of difficulties with the lectures, please don't hesitate to let me know. Okay, bye everyone, and I'll see you guys on Wednesday at noon.